Last lecture, we talked about the mechanisms of plate tectonic, and this time we're going to talk about the implications of plate tectonics, how plate tectonics affects things that you wouldn't necessarily think that it would affect. So this is in your book, and Kiri et al. Discussed three topics. One is environmental change, one is economic geology, and one is natural hazards. I'm not going to talk that much about natural hazards. We've talked about tsunamis and volcanic eruptions, but we'll focus on the first two. But I'd also like to add some more material about hydrocarbons of the Persian Gulf region and hydrocarbons in general, building off of some interesting aspects. So the biggest environmental change due to plate tectonics is sea level rise or fall. And right now we are very focused on sea level rise, and we talked about it, glaciocene versus tectonocene. And we talked about the fact that right now, with the melting of the ice sheets, sea levels rising at about 3 millimeters per year. And we've defined Eustace, and the term refers to global sea level independent of local factors such as tectonic uplift or subsidence, right? If there's a movement on the San Andreas Fault and San Francisco rises a meter, that's not Eustace, that's local tectonics. Eustace is basically the position of the sea surface with reference to a fixed datum, including the center of the Earth or a satellite orbit. And this term was first used by one of our heroes, Edward Seuss, in 1888. Now, it was first used by Clarence Dutton in 1889, who spelled this as Eustace with a C. But when it was realized that the Greek had no C letter, the spelling of the word has been changed to Eustace with an F, with two S's. So sea level controls continental flooding or exposure, right? When sea level is high, more of the continents are flooded. When sea level is low, more of the continents are exposed. And the percentage of the Earth that is exposed continent or ocean strongly influences climates. Okay. So, as we said before, the eustatic changes mostly reflect changes in the volume of continental ice or the change in the mean age of the seafloor, and perhaps the abundance of hotspot volcanism. There should be a spot in there because all volcanism is hot. All right, so we looked at some of these curves and we remarked on how, that there's pretty good agreement for the more recent times and much greater disagreement back in the Paleozoic. And what we see here also are some glacial events marked with G's. There's one in the Ordovician, there's definitely one in the Permo-Carboniferous, and then there's one going on that started, in the middle Cenozoic. Now, what you notice is that, yeah, there's definitely sea level response, at least on the Exxon curve for the Ordovician and the Carboniferous glaciations, and certainly the more recent one. But there's also a lot of ups and downs that seem to have nothing to do whatsoever with ice volume. For example, high sea level in the Ordovician, at least the Hallam curve, and to a lesser extent the Exxon curve, and also high sea level in the Cretaceous, right? And this happened without any continental ice sheets to melt. There were no continental ice sheets in the Ordovician, most of the Ordovician, and in the Cretaceous for sure. Now, so we talked about the supercontinent cycle a couple lectures ago, and this, we pointed out, controls mean seafloor age. It's so important, though, I think it's worth going over again. So the supercontinent cycle and the Wilson cycle, its corollary, controls mean seafloor age, and the mean seafloor age controls sea level, and we'll talk a little bit more about this. So here we have three idealized configurations of the continents and the oceans in different times. So what we're going on the left is we've got a supercontinent there. It's called Pangaea, and it's surrounded by the Pacific Ocean, or Panthalassa, as we now call it, the world ocean. And the mean age of the seafloor was 53 million years. Okay. So rifting is just starting. There's no new seafloor in those fragments. In the second panel, we see the Atlantic and the Indian Ocean have opened, and so there's a whole bunch of new seafloor being produced and old seafloor being destroyed. So the mean age of the seafloor becomes younger, only 5 million years younger, but that's significant, as you'll see in a minute. And then as the Atlantic Ocean continues to widen, it ages, and the mean age of the ocean gets older again. So here we've got, let's call this normal mean age of seafloor, 53 million years. Then we have a young mean age of seafloor, and then we have an old mean age. So what that's going to do is we're going to have seafloor at normal depth, if you want to, of course, there's going to be differences in elevation, bathymetry of the seafloor closer or farther away from the ridge, but considered as a whole, the average depth of the seafloor will be normal. Now, when the seafloor gets younger, the seafloor is going to have a mean depth that's shallower. And when it gets older again, it will be deeper. So that's the water, the seawater just follows that. So when you have normal mean age of seafloor and seafloor at normal depth, you're going to have a normal sea level. When you have very young oceanic crust mean age, the seafloor will be shallow and sea level will be high, flooding the continents. And when the oceans get old, you'll have deep seafloor and sea level will drop. It's that simple. All right, now here's what we're looking at. We've seen this curve. This is the Parsons and Slater curve, or GDH1, or whatever you want to call it. We're looking at the depth of the seafloor as a function of age.
I apologize, but I mean, if we're creating and destroying the same amount of seafloor every year, I'm not sure why the age would change.
Well, let's go back and take a look. So you can see that, this is one ocean.
Right.
And here we've added a bunch of new oceans.
Yeah, but
which can't be very old, at least at the beginning, but they will age.
The age of the other of the other stuff should have been higher than 53. It would have aged in the meantime too.
Well, I mean, remember, some of it's going to be subducted as well. So this is a very simple representation of what's going on. We assume that the Pacific doesn't really change its mean age over time. Obviously, a more sophisticated analysis would show that was wrong in detail. But for the purposes of explaining what's going on through the supercontinent cycle, I think it's a valid way to look at it. You're right that the Pacific seafloor would have aged after several million years. But again, some of that's going to be subducted, especially the older crust. And we can't know exactly. I mean, especially if we're talking about Pangaea, because we don't have a record of seafloor age back that old. We only go back to the Jurassic. Is that?
Yeah, I'm just still struggling. I'm still struggling though if we create as much as we destroy every year, why it's going to.
Because we went through the supercontinent cycle. At the beginning, we're creating more new seafloor. There's new oceans there, right? And they're all very young.
Okay, so you're just saying we're creating more, but then we wouldn't be destroying more then too.
Oh no, it's so there. We can assume that the crustal production rate is similar, and the crustal destruction rate via subduction is similar, but it's going to preferentially remove the older seafloor of the Pacific. There's no subduction zones in the Atlantic or the Indian to speak of.
Okay.
But
Sorry.
of course, it's more complicated than that. No, it's an important point, and I don't mind discussing it further. Not at all. All right, so this is showing you what that mean age would be. Now, again, this is not saying all of the oceans are these ages. It's saying that if you integrate, average the age of the seafloor at different stages, in one stage the mean age will be older, and then other it'll be younger, and the third it'll be in the middle. And here we're seeing the different elevations, right? For 59 million years, the mean age of the mean depth of the seafloor is on the order of, over 55,000 meters. At 48 million years, it's below 5,000 meters. So this is a very steep part of the curve, and changing ages of the seafloor is going to have a big effect on the depth of the seafloor. And just like getting in the bathtub, the water level is going to rise. Does that make sense? Okay, so young seafloor tends to lead to transgressions, and we're talking about younger mean age of seafloor leads to transgressions, right? When the sea level rises, that's a transgression, and when sea level gets older and subsides, that leads to a regression. So transgression and regression may be familiar to those of you that have taken sedimentology, but that's it in a nutshell. All right, so let's look at a very simplified, this is a very simplified diagram for sea level. So sea level here is low, sea level here is high, and we're looking at a sort of a smooth curve. And you see that sea level is relatively high in the Ordovician, and then it drops in the Permo-Triassic, and then it goes up again in the Cretaceous. And you'll notice that this is one of our supercontinent cycles. Greater Gondwana land sort of breaks up, or begins breaking up in the beginning of the Paleozoic. Pangea forms at the end of the Paleozoic. And you can see just from showing those there that sea level is low when the supercontinents exist, and it rises between the supercontinents. So we can call this first order tectonoeustasy, right? First order tectonoeustasy is controlled by seafloor age, and thus by the supercontinent cycle. All right, this is something that people who are worried about rising sea level never consider, because these rates of changes are incredibly slow. So in the Cretaceous in Texas, if you had the good fortune to live a few tens of millions of years and stood where Dallas is now, you would see the beach slowly moving towards you. And when I say slowly, we'd have to calculate what it is, but it's nothing like the rates of change that you see when glaciers melt or form. Those are very rapid changes by comparison. 3 millimeters per year, like we're experiencing now, is a very rapid change in sea level. Maybe not from the human perspective, but from the geological perspective. The rates of change of tectonoeustasy are going to be on the order of less than a millimeter per year, but they're just going to keep on happening. All right, so let's talk about the Cretaceous. This is a very interesting time in Earth history. Cretaceous sea level, as you see here, and you guys all know the Cretaceous because that always shows up on the midterm and the final, when was the Cretaceous? And you all know it's like 145 to 65 million years ago. More time in the Cretaceous than since the Cretaceous. Okay, so the seafloor was young here, but that's not all that was happening. So let's look at some events in the Cretaceous. So here we've got the geochronological timescale going back to the beginning of the Mesozoic, right? And then these are lower Triassic, middle Triassic, upper Triassic, et cetera, et cetera. These are Cretaceous stages. We'll talk about the Turonian, Campanian when we talk about the Austin Chalk. And then here's the tertiary. So here we've got the Exxon curve, right? High sea level, low sea level. And here we see sea level coming up the way they interpret it, with the maximum here in the late Cretaceous. And over here we see, when seafloor spreading started in the what we call the Atlantic domain, which includes, everything between the old world and Africa and the new world. So we start off forming the central Atlantic about 100 and what is that, 70 million years ago, and then the South Atlantic begins to open, and then the South Atlantic continues to open, and then the Iceland and Norwegian Green Sea. So you're seeing all of these ocean segments opening. So you're getting younger and younger seafloor forming at that time. Okay. And as we see, seafloor production reached a maximum during the Cretaceous. So this, you might think this might be sea level, but it's not. This is seafloor production in square kilometers per million years per year. So today, most people assume we're generating 2.5 to 3 square kilometers of new seafloor a year, and we're subducting the same amount, obviously. And so these are different studies that tried to reconstruct, because we have the magnetic anomalies for the Cretaceous, how seafloor production happened. And they all agree that during the Cretaceous, seafloor production was higher. Comins argues it was between 5 and 6 cubic square kilometers per year. Gaffin 87, a little bit less. Ingebretson a bit less, but in all three of them, Cretaceous seafloor production rate was higher than it is today, which is going to result in a younger age of the seafloor, right? So because mean seafloor age reached a minimum at this time, so the mean seafloor depth reached a minimum, and continental flooding reached a maximum. Now, another thing that happened in the Cretaceous was an increase in hotspot volcanism. These are mantle plume activity. So this is the onset of the Cretaceous superplume, which is, if you look at a map of the Pacific Ocean, there's one outside of my office, actually two. One of them is the old Tharp and Heezen map, and the other one is more modern one. You'll see that the Western Pacific is much more pimpled. It's got a lot more seamounts than the Eastern Pacific. And that is the preservation of this Cretaceous superplume event. Okay, so and around 120 million years ago, things just started going off in the ocean. And not only in the ocean, that's also when the Arkansas alkalic province was formed. So you see evidence of sort of small scale volcanism on all of the continents during the Cretaceous. So that would also cause sea level, displace seawater and cause sea level to rise. So, there was just a lot of things going on in the oceans that pushed seawater up on the continents. Now, are there other ways that we can see this? Do we have to just look at sea level? And your book talks about a very interesting thing that I never heard of before reading the book, which was the effects of seafloor spreading on limestones. So let's keep in mind we don't have seafloor magnetics older than about 180 million years ago. So we can't say much with much confidence about what was happening in the seafloors then from the seafloor magnetics, because they don't exist. But we can use the composition of limestones. And when I saw that, I go, what? But let's talk about it. So limestone, as you know, is mostly calcium carbonate. And calcium carbonate, the mineral, can be one of three polymorphs. It can be low magnesium calcite, high magnesium calcite, or aragonite. So calcite is trigonal, and aragonite is orthorhombic. They're different minerals with the same chemical composition. We call them polymorphs. And magnesium can substitute for calcium in the lattice. And if there's a lot of it, we call it high magnesium calcite. And if there's not much of it, we call it low magnesium. So the formation of these carbonates is sensitive to the composition of the seawater they formed in equilibrium with. So seawater that is rich in magnesium favors either high magnesium calcite or aragonite, and seawater that's poor in magnesium favors low magnesium calcite. So you're getting the idea that we're going to be talking about, the abundance of magnesium in seawater through time, and that's what we are. So how does plate tectonics control the abundance of magnesium in seawater? All right, this is by hydrothermal activity near mid-ocean ridges. So if you what happens with hydrothermal activity, is the seawater percolates along faults and then heats up and interacts with the rocks it passes through and alters them. So the seawater plus hot oceanic crust leads to this hydrothermal circulation, generates these black smokers that are so common on science channels, and it also produces altered oceanic crust. Now, that alteration is what is responsible for the magnesium budget in the oceans. So magnesium from seawater is added during hydrothermal alteration of basalts due to hydrothermal circulation to make chlorite. Chlorite's a mineral, and it's the reason that green rocks are green. They have a lot of chlorite. And chlorite is up to 25% magnesium oxide, which is a lot compared to basalts and stuff. So taking the magnesium out of seawater as a result of this process decreases the magnesium calcium ratio of seawater, and this is reflected in the composition of the carbonate sediments that are deposited at that time. So aragonite and high magnesium calcite have high magnesium contents, and they tend to form when seafloor spreading is low, which is when hydrothermal activity is low, and the magnesium contents of seawater is high, because the hydrothermal activity doesn't take the magnesium out of seawater to the extent that it does when that activity is high. Does that make sense? It's slightly complicated, but it's relatively straightforward. All right, now this is just showing you the relationship between hydrothermal activity and spreading rate. So these are hydrothermal plumes that can be monitored along spreading segments. And so here we've got this full spreading rate, right? We're going from slow spreading to intermediate spreading to fast spreading. And what we see is there's a higher fraction of hydrothermal plumes, which means hydrothermal vents, on the ridge if you have faster spreading. And that makes sense because faster spreading ridges have a lot more magma. It makes sense that faster spreading ridges would have more hydrothermal activity, more plumes. Okay, so it makes sense that there's this strong relationship between seafloor spreading rates and the abundance of hydrothermal activity. All right. So if there's more seafloor spreading, there should be more seafloor hydrothermal activity. So less seafloor spreading result means less hydrothermal activity, which means more magnesium in seawater, which means this is a time when aragonite or high magnesium calcite form. And we call that a time of aragonite seas. Contrast that with the times when there's more seafloor spreading, there's more hydrothermal activity, there's less magnesium in the seawater. That is a time we call calcite seas. Does that make sense? All right. And as we noted, seafloor spreading reached a maximum during the Cretaceous. So we would expect this to be a time of calcite seas, right? Because the magnesium is being really stripped out. Yes, Clint.
Right. And I would point out that this turns up in the paleontology or Earth and Life class where you're looking at, excuse me, seashells. And there's and also corals. And so the amount of magnesium in them is significant in telling how old they are and so on. Back to you.
Yeah. So, okay, so we've got this relationship between limestone compositions and sea level. So if you look at something like this, where we're seeing the sea level curve, this is kind of complicated because this one is showing sea level rising, and that's being shown on the right side, relative sea level in meters. So today we're here at what is that? Normal sea level, and it'd be better if it was colored. And these blocky lines, that's the area of continents, right? So if you look at the scale for the non-marine area, it goes from 110, the minimum, to 150, the maximum. So right now, we're, the area of continents is on the order of, what is that, 155 million square kilometers. And back in the Cretaceous, the end of the Cretaceous, it was, 2/3 of that. So that, obviously sea level and the percentage of non-marine areas are going to relate. Higher sea level, more continental exposure. So it's a confusing diagram, but I think you get it, right? All right. Seafloor production rates were high in the Cretaceous. Shallow seafloor. Seafloor is, the continental area. The continental area is at a minimum. Sea level is at a maximum. Same time. And we see something like this. This is the Cretaceous Interior Seaway. UTD is down here. And this seaway went all the way up to the Arctic Circle. And at the same time that's going on, we've got orogenic activity over here, the severe fold and thrust belt. We've got Foreland Basin. So this lithosphere is being depressed. That's contributing to the fact that the sea level can come in. There's a lot of things working together, but we have this wonderful seaway, and Dallas is right in the middle of it. This is what Dallas looked like in the Coniacian Santonian. These are Cretaceous stages, which you do not have to memorize, but if you're a Cretaceous, you really work on the Cretaceous a lot, you will memorize them. And that's the Coniacian Santonian. These are called stages. And that was about 85 million years ago. And if we went back in time, we would see a scene like this with, flying reptiles over an ocean with no sign of land on the horizon in any direction. And that we don't really know exactly how deep the Cretaceous Interior Seaway was over Dallas, but it's thought to have been a few hundred meters deep. And at the time that the Austin Chalk was deposited, which every UTD student knows that UTD is built on. Ha ha. All right. So let's look at this book chart out of your book. So there's the Cambrian. There we are today. High sea level, low sea level. We see low sea level. We go, oh, we're not having much seafloor spreading. And we see the magnesium calcium ratio goes up at this time, which is consistent with what we talked about with hydrothermal activity and spreading. And then here in the Cretaceous, you know, when sea level is high and we have fast spreading, the magnesium calcium ratio of carbonates goes way down. So we can talk about these early and mid Paleozoic limestones as being calcites, calcite as forming in a calcite sea. And then through most of the Mesozoic until the Cretaceous, we're talking about aragonite seas. And that would also extend some of the late Paleozoic. And then we go back into calcite seas. And today we're back in an aragonite sea. Okay. So now there's a slight complication that many of you may be aware of, which is dolomites. Dolomites are unusual because they require special conditions to form. So they're not as diagnostic as primary limestones that are either calcite or aragonite. If you see dolomite, then this scheme doesn't work. But don't worry about that complication. There may be a question on the midterm about aragonite seas, dolomite seas, aragonite seas, calcite seas, and what that means, what you can infer about seafloor spreading from that on the midterm. All right, now let's discuss plate tectonics. Plate tectonics, forgot a T there, and climate, and how these concepts help us understand oil and gas. All right, so yes.
I apologize, but going down one of my rabbit holes as usual. I mean, I'm kind of blown away that those ratios change that much. And do you see it? I mean, if it's happening in the area of seafloor spreading and hydrothermal vents, I mean, is that changing the calcium magnesium ratios half an Earth away? You know, 5,000. It diffuses so fast that it affects 3,000 miles away, and
it takes years for currents to distribute things around. But these, there's a branch of geochemistry that is concerned with what we call residence times of different elements. So some elements, when they get in seawater, they immediately precipitate as solids. Iron is a good example of that. It was only very recently that we had sufficient analytical precision to measure the iron concentration of seawater. That's because its residence time is so short. In contrast, things like sodium, they have very long residence times. And calcium and magnesium are more like sodium than they are iron. So they don't precipitate out into solids right away. They're quite soluble in seawater. So the mixing times of the ocean are relatively short compared to the residence time of those two elements. Yes, Clint.
And famously, carbon dioxide mixes really fast, and therefore, if there's more CO2 in the atmosphere, it immediately acidifies the ocean or increases the acidity of the ocean, which is probably a bigger problem than warming.
Yeah, well, that's a different course. All right, now let's get back into oil and gas. So let's talk about it. So we're going to talk about oceanography now, and we're going to specifically talk about the bottom water. So bottom water is the water that occupies the lowest part of the oceans, and the formation of bottom water is tied to the climate. So today, the world's oceans, the bottom water is formed in the continental shelves around Antarctica. And what happens there is seawater freezes when it's winter, And what that does is the ice has less sodium in it than the water it forms for. So it basically squeezes out the brine, and that brine makes the water dense, even denser than it is. It's cold water, and water reaches its maximum density very close to the freezing point. And then you add these cations to it, like sodium, and it increases it even more. So this is the densest water that is formed in the earth, is formed around Antarctica. So the other thing it does is it brings, because it forms very near the surface, it brings a lot of dissolved oxygen with it. So that deep ocean water is dense, cold, and oxygenated. And it goes all over the world. Now, this sort of shows this is where the deep water forms, and oceanographers have been studying this for a long time, and goes around the circum-Antarctic, and some of it goes up into the Atlantic, some of it goes off into the Indian, some of it goes off to the, Pacific, but that's where the world's deep water forms, right? It's called the Great Ocean Conveyor Belt. It's this very cold and salty deep current, and then it's thought to rise in the North Pacific and in these regions like that. So that's what's making the bottom water today. And for that matter, anytime we have an ice sheet on a southern continent or a northern continent, it will probably make the bottom water the same way. But how do we make bottom water when there's no ice sheet? This is a very interesting problem in paleoclimatology. And it seems likely that during greenhouse episodes like the Cretaceous, when there were no continental glaciations, that the deep water formed differently. And we can't imagine how it formed. Maybe it just stayed there a long time without being refreshed like modern deep water is. And if so, the oxygen would be very depleted as a result of respiration. There aren't very many creatures down there, but there are some. All right, so this is a modern ocean O2 and CO2 profile. So this, above this dashed line, this region is well mixed. It equilibrates with the ocean because of winds and waves. This is where phytoplankton like to live. So they're producing oxygen all the time. This is a very oxygenated zone. And then once you get below this zone, the oxygen falls off tremendously. And the oxygen at the bottom of the ocean is basically controlled by the Antarctic deep water today. And CO2 correspondingly is very low up here in this mixed layer. And it increases very, very dramatically with depth. Okay? So that's the present situation. It would look quite different during the Cretaceous when there was no continental glaciation to generate these dense, cold, oxygenated brines. So let's look at the modern ocean and during icehouse events. So we got frigid polar regions that are creating deep bottom water, and these are it's a well mixed ocean because you're bringing in oxygen to the bottom, and this is slowly going to heat up and it'll mix. So this is cold, dense oxygenated water forms on the polar shelves, sinks to the bottom of the ocean, and keeps the deep waters oxygenated. What's going to happen to any organic carbon that settles into a basin in this ocean? Well, the carbon is going to be converted to CO2 by respiration. There's going to be bottom creatures that like to eat the mud and get the organic material out, and you'll have very little organic carbon buried. And as you know, organic carbon has to be buried in order to get oil. Now, what happened in the Cretaceous during a greenhouse Earth? The polar regions are not ice shelves. We know there were dinosaurs in Alaska in the Cretaceous. So the absence of polar ice results in no sinking of cold oxygenated water. The buildup of CO2 in the deep water leads to periodic anoxia, which is a way to talk about no oxygen in the deep water. And it also builds up sulfur contents. So you kill off biota, and this preserves organic matter that sinks to the bottom of this stagnant ocean. And this is when black shales get deposited. So here is, we talk about marine anoxia. Yes, Clint.
And that would be anybody here live in Grand Prairie? If you do, you live on top of some of this.
Yeah, I'll be talking about that.
Okay.
So here we're looking at the Black Sea. This is a profile through the Black Sea. This is the Straits of Bosporus near Turkey, Turkey and Greece. Water comes in and out, but that's, so the top of the Black Sea is oxygenated, but so below a certain depth, you've got anoxia. So here we're looking at, this is salinity. So this deeper water is denser. That's why it's there. And here's the percentage of oxygen, very oxygenated at the top. And then I'm not sure why this would go there. That I would think that it basically goes to zero at that anoxia zone. And so anything that, like, people have been finding old Greek ships in the bottom of the Black Sea because nothing can live there to eat them. So that's an analog for the Cretaceous oceans is the present Black Sea. So here's oxygen and life. So here we've got, this is what we get in, this is milliliters of O2 per liter of water. This is what we get in the well-mixed zone, winds and waves, somewhere between 6 and 8.5 milliliters of oxygen per liter of water. And then as the oxygen content goes down, benthic animals can live in oxygen concentrations as low as about 1 milliliter of oxygen. And then below that, benthic life, that's life on the bottom, decreases sharply. And then below about 0.3 milliliters per liter, you don't have any deposit feeders, these scavengers that eat the mud and bury into the mud. And basically below 1/10 of a milliliter per liter oxygen, all of the bottom critters die. So everything is preserved that falls to the bottom, organic matter. So sediments deposited during times of anoxia are called black shales. So they're black because they're rich in organic carbon. There's no bioturbation, which happens when animals dig into these and deposit feed on them. Nothing can live in them, so these are completely undisturbed sediments. There's lots of sulfur and pyrite. People like to go out and collect pyrite in Dallas near the Eagleford. And these are the very important source rocks for oil deposits. So, hydrothermal activity also contributes to depleting the bottom water oxygen. So if you have more hydrothermal activity superimposed on this general cause of anoxia, you're going to have a lot of sulfur coming out of there, and that's going to contribute to things like pyrite formation. So what we can see in the geologic record here, we're looking at the Cenozoic, the Cretaceous, that's the late Cretaceous, that's the early Cretaceous, the Jurassic, right? Late, middle, and early Jurassic. There are things that are called oceanic anoxia events, times when black shales are especially common. And there are 3 of them on here. There's this early one, this early Toracian, sort of early Jurassic, TOAE. We could call it the Poseidon-de Schiefer event, which I never heard of before, and you will not be asked to remember. Then there was one in the early Cretaceous in what's called the Aptian stage. This is the early Aptian oceanic anoxia event, which is sometimes called OAE1A, sometimes called the Sully event. That was at about 120. So this is about 180. This is about 120. And then there's one in the Cenomanian Turonian. This is OAE2, sometimes called the Bonarelli event. This is the one that we know in Texas. So let's look at the local evidence for Cretaceous seafloor spreading. And that's the Gulf series, which underlies most of the eastern part of the Metroplex. So this is a very simple map. These are the counties of the Metroplex. Here's UT Dallas up here north of Dallas. And we've got here off to the west, so there's mineral wells. That's Permian sediments over there, and then Pennsylvanian sediments from mineral wells and Bridgeport to the west. And then the next, you got this long unconformity, you know, the Pennsylvanian was about 300 million years ago, and the early Cretaceous was about 120. So it's about 180 million years when this was land or something was eroded. And then there's two series in the Cretaceous. The early Cretaceous series is called the Comanchean, and that basically goes right up to the boundary between Fort Worth and Arlington. And then the Gulfian, it goes from basically Arlington over to Terrell. So this is the area of interest, the section of interest, this late Cretaceous section. So we can look at this cross section, a very simplified one I made years ago. And this is sort of what you would see if we could, you know, drill a hole underneath UTD, you know, we'd go through the full, this is the Cretaceous section gently dipping off to the east. The dip's greatly exaggerated here. So Dallas itself is built on the Austin Chalk, you know, and we can discuss that. But here's the Gulf series, the Gulfian series, you know, the Woodbine sandstone at the base, then the Eagleford Shale, then the Austin Chalk, and then the Taylor Marl and other units off to the east. Okay, we'll go back. So the Eagleford Shale, which we'll be talking about, was deposited during OAE2. So this is the Eagleford Shale in Dallas. This is what it looks like when you just dig it. You know, it hasn't had a chance to weather. This is what it looks like when it's weathered. You know, all of this organic matter and just ugly black stuff has been weathered and bleached, and that's what it looks like. Very, very poor outcrops, very, very poor foundation material for construction. All right, so the Eagleford has a lot of organic carbon, 1 to 10%. So this is sort of the range of organic carbon in the Eagleford. So that's 1 weight percent. You know, this is a log scale, so that's 100% organic carbon. So what would that be? Coal or something? You know, it ranges tremendously. You know, the Austin Chalk has a much lower content of organic matter, these circles. And these are, you know, this and this, these are Eagleford at Waco and Austin, you know, they're much higher. Now, this is a really great story of, you know, Dallas and Texas. So here we are in the, that's the border between Texas, Arkansas, and Louisiana. And this is going from the East Texas Basin, which we haven't talked about, but it's over there, across the Sabine uplift and into the northern Louisiana salt basin. And this is what the unconformity on that Paleozoic basin looks like. It's kind of an uplift, and it's deformed all of the overlying rocks to the point that there's actually an unconformity between the lower Cretaceous and the upper Cretaceous. And there is this sort of pinching out of the Woodbine sandstone, which is a great reservoir rock. And the oil that was produced probably from the maturation of the Eagleford, which actually sits on top of it, but could be down section, was filled to the brim when in the 1930s, when Dad Joyner just went out there and drilled a wildcat well, and then the famous story of H.L. Hunt meeting Dad Joyner at the Adolphus Hotel over a plate of cheese and crackers and convincing him to sell all of his rights. And of course, Hunt became one of the richest men in the world, mainly because of the oil from the East Texas oil field. It changed Dallas completely. Now, so the Sabine uplift and stuff is way up here, but now we've got this Eagleford play, which isn't a conventional trap like East Texas, but is an unconventional play here. And you can see here in red, I think green is oil and red is natural gas. Correct me if I'm wrong. And this play just exploded around 2010, 2011. And it is presently, it peaked at about 5 million barrels per day, but it's still, no, it peaked at, it looked like a couple million barrels, but it's still producing on the order of over 1 million barrels per day from this play. Yes, Clinton.
Pleased to say that my company was big in the early days of it and pretty much leased up Dimmitt County, which we then sold to Chesapeake, which then tried to sell it to Chinese National Overseas Oil Company. And then people said, like, oh my God, it's Dimmitt County, and so on and so forth.
Which one is Dimmitt County?
Square one next to Maverick County. So it's almost on the border on the left side.
That one?
Yeah, that one, or the one above it, I forget.
No, that's Zavala. Zyma.
Okay. Yeah, so I guess it's
somewhere down there.
Yep.
Yeah, so the Eagleford Shale continues to be an important resource. I mean, this is obviously much smaller production than out of the Permian Basin, but more than 1 million barrels per day is nothing to sneeze at. All right, so let's move on to another topic. Yeah, you still have your hand up, Clint?
One more thing, which is that if you look at North America from at night with the lights on, you'll see this belt of light. And it's not towns, it's the Eagleford production facilities.
Oh. Is it flaring or is it actually electricity?
Just electric lights.
Yeah, interesting. All right, so let's talk about the Persian Gulf. This is kind of an interesting story that, and in an interesting region, right? This is a collision zone, and the countries on both sides of this collision have oil, and one has to wonder, why is the Persian Gulf so rich in hydrocarbons? So let's talk about Saudi Arabia, which has legendary reserves. This map probably needs to be updated because I believe these are conventional reserves, and the unconventionals have obviously changed everything. All right, so these are the oil and gas fields of the Middle East. So Saudi Arabia, this is Precambrian outcrop on the western side, adjacent to the Red Sea, which is a incipient, ocean basin, and we still have the ridge, the rift flank uplift, very well developed in here. A lot of volcanic rocks in this flesh color. And then over here in Eastern Arabia, we have a lot of sediment. It's sort of a gently dipping slope off to the east. This is Iran. Here we've got a lot of structure, fold and thrust belt. We've talked about the Zagros as being a spectacular example of an on-land accretionary prism. And we can see from the oil and gas fields it's very, very different orientations. So the great oil field, including the Gower field, which we'll talk about in greater detail, are sort of oriented north-south in Saudi Arabia. And then they get completely reoriented into a northwest-southeast trend in Iran, in Zagros, and then up into Iraq, right? So there's a plate boundary in here. We've talked about this boundary between Arabia and Eurasia. They call it the Arabian Gulf. I prefer to call it the Persian Gulf, but you know, this is basically sort of the trench equivalent. We could call it a foreland basin. If we did call it, it would be a peripheral foreland basin. It's definitely not a retroarc foreland basin. So this would be a peripheral, and you can almost see where the plate boundary is because that's where the oil fields change trends, right? Right around in there. Okay, so these are the plate motions for Arabia and Eurasia. And so that's 20 millimeters per year. So this part of Arabia is going north at 22 millimeters per year. This part's going north at 16. So the pole of rotation's off here somewhere. Okay, and then here's the Zagros. This is the Mesopotamian floodplain, right? Where the Tigris and Euphrates flow down from these highlands. And then Arabia. So we're not showing any oil fields on here. We're just sort of looking at the main tectonic elements of this system. Now, this is sediment thickness on the Arabian plate, and this is Arabia. Now, they're drawing the plate boundary kind of in a funny place. It's, that's sort of on the north side of the Persian Gulf, and then going up north of Baghdad and linking up with the collision zone in Turkey. A lot of this stuff is sediment thickness that's not on the Arabian plate. Where we stop measuring the Arabian plate is a good question. But definitely this is Arabian plate, right? And we can see that in general, the top of the basement interface is 2 kilometers above sea level right here. And then it gets deeper and deeper, very quickly. The top of the basement here is maybe 11 kilometers down. That's, sort of a classic look for a foreland basin, very deep on the side nearest the master fault, which is this thing, certainly, right? And you can see these structures are affecting the sediment thickness. Here's one going through Qatar. There's a basin down there. There's an uplift. So these structures are unrelated to this structures. And we'll talk about what was responsible for making this structural fabric of Arabia. So why is there so much oil in the Persian Gulf region? So number one is rich source rock and lots of it. So what you had in Arabia behaved as a continental shelf for a very long period of time. So from about, latest Precambrian up until a few million years ago, the Eastern Arabian plate accumulated up to 15 kilometers of sediment, generally in a marine setting as a passive margin on the northern flank of Gondwana. The sediments formed several petroleum systems. The best is the Arab carbonate reservoir, which is interbedded with several anhydrite layers, though they make very nice seals, and sourced by a very thick, organic-rich intrashelf conglomerate carbonate called the Hanifa Formation. This system alone contains 500 billion barrels of original reserves in Saudi Arabia, Qatar, and United Arab Emirates. And it also includes the supergiant Gower field, which had 200 billion barrels original. So simply stated, the Arabian Plate lay next to oceans for most of the Phanerozoic time when it collected lots of petroleum-related sedimentary rocks. So, then the question is, why was the continental area of Eastern Arabia so close to sea level all of that time? Why was it just below there? And I'm not sure we're going to get into that, but that's something I worked on for a while. All right, so there's 4 important Persian Gulf source rocks. So the main source rocks are Neoproterozoic carbonates and shales in Oman. These are one of the oldest petroleum systems in the world, but they're very minor in volume by Middle Eastern standards, less than 1% of the oil we're talking about. Then there are the Lower Silurian deep water black shales. This source rock goes all the way over to North Africa. It's especially significant in sourcing the largest gas field of the world in Qatar. The main source rock is this Jurassic Hanifa formation I just mentioned, which was deposited on a shelf basin. And then there are other source rocks of latest Jurassic, early Cretaceous, deep water carbonates at 140 million years. So sedimentary rocks of Eastern Arabia are shallow marine platform sediments, carbonates and evaporites, cycles of porous carbonates sealed by anhydrite, which is in sort of the Arab A to the Arab D. So here's the late Jurassic Arab sequence, which is very important. And there's the Hanifa, right? So these are very well in that part of the world. All right, so here we're looking at sort of a cross section across Arabia into Iran, across the Persian Gulf, going by the tip. And here's sort of this sort of northeast dipping section, and then here we're starting to see these structures. These are sort of some places there's Precambrian basement poking up, but these things are huge oil traps. So there's the Qatar Peninsula, the Daman Dome, that goes the Discovery Dome in Saudi Arabia. So people have broken this up into the stable shelf, and then the unstable shelf, and then this region over in Iran, which they're calling zone of marginal troughs, but really we could call it the accretionary prism. This is a huge section of carbonate rocks, and as it goes into the Persian Gulf, it's entering the subduction zone beneath Iran, right? And you can start to see the deformation that you would expect in front of an accretionary prism there. Now, this deformation, mild deformation away from that convergent margin, happened a long time ago. It's called the Hercynian event, and that's a European term for the 300 million year old event associated with the collision to form Gondwana. In our part of the world, we talk about the Wachitas. So if European geologists came over and wanted to see the Hercynian event in Oklahoma, you'd take them up to see the Wachitas, or maybe you'd take them out to West Texas and show them the marathon. They're the same age, but this mild Hercynian late Paleozoic deformation was responsible for generating these gentle structures that contain so much oil. So these are the structural and tectonic features of the Arabian Plate. So these salt basins, these are about 540 million year old salt basins, right? There's the Hormuz salt basin. There's one in Oman. This is the Oman oil fields. And so you can see these north-south Hercynian structures very well in the outlines of these uplifts and things like that. Okay, so Here's the structure, and here we've got the structure of the oil fields. So you see these north-south anticlines. Here is the outcrop belt. There's the Precambrian. There's the Paleozoic, Triassic, Jurassic, Cretaceous exposure. This is all younger rocks. And these are the structures that are controlling the major traps for the oil of northern Arabia. And Qatar is a peninsula that's also structurally controlled, clearly. This is the Goward oil field. So this is 100 kilometers. So this oil field is on the order of 250 kilometers north-south. And oil was discovered in Arabia in 1932, but it was 1948 that the elephant of all oil fields, the Gowar field, was discovered. So 300 kilometers long, 27 kilometers across, cumulative oil production thought to be 55 billion barrels. And if you put it on a map of Louisiana, it looked like that. That's an amazing oil field. Okay, so this is the structure going from west to east across Saudi Arabia and into Qatar. Let's see if we can find out where that would be. It would be something, like this, going across that. And you can see these gentle structures, these Hercynian structures, right? That's where the oil is trapped. And here we have a seismic reflection profile. Yes, John.
Is it mainly trapped by salt then over there?
Well, I don't know the details of the trap, but I imagine that the anhydrite seals in the Jurassic are the most important because the salt is older, and the thick bedded salt is late Precambrian, but there's plenty of seals in that Hanifa formation, the Arab A through D sequence, as I understand it. So this is the structure across the Gower field, and you can see how gentle it is, right? There's the Triassic, very gentle doming. And this is what you see, the structures you see. This is the structure. All of this faulting is especially active in the Carboniferous, so associated with the Hercynian. Some of it looks like it's been reactivated during the Permian, but since then it's just been sediments being piled on these things. So now that's the story from Arabia, but what about Iran? So, here we've got, Arabia over here. That's Qatar. This is very gently deformed and full of oil. Here we've got Zagros. This is very complexly deformed and also full of oil. So it's a very interesting story that we're not really sure what's going on. So this is what's happening, right? The Arabian plate is being subducted beneath the Eurasian plate, and the Zagros Mountain are sitting in the position of the accretionary prism, and the Mesopotamian foredeep is sort of sitting in the position of trench fill. And you got earthquakes, right? This is behaving like a subduction zone, except pretty much at sea level because we're dealing with continental crust and continental crust. Now, this is what I think is the best explanation, and it's an old one, and it hasn't really been followed up at all. But basically, here's what's happening. This is, okay, it's called oceanic crust, but let's just call it Saudi Arabia. And Saudi Arabia is being subducted And that stuff is going down, and that includes the oil. And this stuff is going down, and it's getting squeezed. And as you know, there's very low geothermal gradients, and it's getting squeezed. And I think it's rising back up and getting caught up in sort of a second episode of trapping in Iran. And when you look at the reservoirs in Iran, they're very different than the reservoirs in Arabia. So here's the subducting Arabian plate, and then there's some of the salt underneath. This is some of that Neoproterozoic salt. And then here are the structures. This is the Upper Permian regional seal. This is the Upper Jurassic regional seal. And this is the Miocene regional seal. And all of them seem to be filled, you know? So gas is, or green is oil, red is gas. This is the non-North American convention. So these are oil fields. These are gas fields, right? It's the other way around in North America, where green is a gas field and oil is red. So this is what the sort of structure of Iranian traps look like. Very different than those of Arabia. But the general idea that the oil in Iran is basically just getting squeegeed out of subducted Arabia is very attractive. Now, this is the oil in Iraq, which sort of continues this trend of in Iran. It's very similar. It's all oriented like that. So this is Kurdistan up here. So that's why the Kurds and I think Honda Oil got very active in exploiting this. These are all sort of, you know, accretionary prism kinds of traps in there. So anyway, that's where we are. That's the lecture. And I find it extremely interesting. I would love to find someone that knows, you know, more about how petroleum is fingerprinted, because then presumably you could fingerprint all of the Arabian oils and compare that with the fingerprints for the Iranian and Iraqi oils and test the hypothesis that the oil of those two regions is just squeegeed out of the Arabian oil, which I think would be a very exciting research project. But I know, let's see, there's next to nothing. I could say I know next to nothing about organic geochemistry of oil, but I think more correct would be to say I know nothing about the organic geochemistry of oil. But I find this tectonic situation and this general scientific problem to be very interesting. So that concludes the lecture.